everyone. This is going to be a video for Module 13 in physics. And that module is going to cover Coulomb's law and it will cover the electric field. So let's start by reviewing some information that I'm sure you all know, but it's good to review it. So you know that an atom is made up of protons, electrons, and neutrons. And we know that, also that protons carry a positive charge and electrons carry a negative charge, and neutrons are neutral. They do not carry a charge. So since in an atom the number of protons and neutrons are equal, so the number of protons and electrons are equal, so they cancel each other out, and that means that an atom has no net charge. Okay, so all of that should be review for you from chemistry. So atoms have no net charge, but then you probably also remember from chemistry that an atom can gain or lose an electron, gain or lose electrons, and then it becomes an ion. So if an atom gains an electron, then it's gaining a negative charge because electrons are negative, and so this would be a negative ion. And if an atom loses an electron, so if it loses an electron, it's losing a negatively charged particle, and therefore that would be a positive ion. You should remember that like charges repel and opposite charges attract. And in class, the last day of class, we'll do some simple experiments to demonstrate this, but the more the charges that is on something, the greater the repulsion or the attraction. So if we take two balloons and rub those balloons in your hair, and both of those balloons both get they pick up a lot of negative charges from your hair, then when you try to put those balloons together, they will repel each other, and the more negative charges that are on those balloons, the greater will be the repulsion between them. And we'll deal with that concept a little bit later when we start to work through problems. Okay, a couple of terms that you should think about with regard to electric charges. So a conductor is something in which it's a substance in which electrical charges flow freely. Or flow easily. And most metals are good conductors. There are other things that are good conductors too. Your body is a good conductor of electrical charges. Water is a good conductor of electrical charges. And then we have an insulator. And an insulator is a substance through which charges cannot flow. And most of your non-metals are not good conductors. They are insulators. With regard to electrical charge, we have the law of conservation of charges. So in the same way that we have the law of conservation of energy, we have the law of conservation of charges. And this law states that the amount of electrical charge in the universe is constant. So in other words, if one substance loses electrons, another must gain them so that the qualifications of the law of conservation of charges is maintained. In terms of charging objects, there are two ways that you can charge things, and one is charging by conduction. And again, we'll do an experiment that will demonstrate this. But when you charge something by conduction, you cause it to take on an electrical charge so you charge it by having it make contact with an object that has an electrical charge. Charge it by having it make contact with an object that has an electrical charge. So the key here is that it makes contact. So you are charging something by touching an object to it that has an electrical charge, and then you're allowing the charges to flow between the object that is charged and the object that is being charged. One if you've ever walked up, if you ever touched somebody and you get an electrical shock, that is charging by conduction. So the person that you touched had an electrical charge, and when you touched that person, some of that electrical charge moved to you, and it happened by direct contact. Okay, so by touching. And as I said, we'll demonstrate some of these when we get together for lab. So then the other type of charging is called charging by induction. And with charging, when you charge an object by induction, you charge an object without direct contact between the two objects. So again, we'll demonstrate this when we get together for labs, but when you charge by induction, the main way that it happens is you can bring a charge close, you can bring an opposite charge close to it, and that causes the charges that are in the object to move away. So you repel them, and then that creates the electrical charge. So again, the key here is that there's no direct contact, and we'll demonstrate that. We'll actually make an electroscope, and we can demonstrate how you can cause an object to have a charge without it coming directly in contact with a charge, but by bringing it near to a charge and causing those charges to move. If we look at the electrical force between two objects, we know that the amount of force is related to two things. One, it's related to the amount of charge on the two objects. And secondly, it's related to the distance between the two objects. So the greater the amount of charge, the greater will be the electrical force. So if you have two objects and they have a greater charge on those two objects, you will have a greater electrical force. And then with regard to distance, the closer the objects are to each other, the greater will be the electrical force. So what we've just said is that the electrical force is directly proportional to the amount of charge, and it's inversely proportional to the distance between them. So before we go any farther, let's, since the title of this chapter is Coulomb's law, let's go ahead and define a term, which is electrostatic force. Okay, so when something is static, it's not moving. So an electrostatic force is the force that exists between two charges at rest. And a Frenchman I can't remember his first name, but his last name was Coulomb, studied this force that is generated between two charges at rest. And as we said, the force that is generated is based on the amount of charge and also based on the distance between them. And so Coulomb was able to come up with a simple mathematical equation to express this relationship between, or to express the force that exists between charges at rest. And that Coulomb's law is K times Q1 times Q2 divided by R squared. Okay, so K is a constant, which we'll see in just a moment what that constant is. Q1 and Q2 is the charge, the amount of charge on the two particles, and then R, as we've seen before, is the distance between the two charges. Okay, so if you look at the equation, you see that the force is directly proportional to the magnitude of the charge, and it's inversely proportional to the distance between them. So the greater these charges, the greater will be the force, and the closer the objects are together, the greater will be the force. The farther those objects are away from each other, the less will be the force. Okay, so the unit for that charge, let me go ahead and write that up. So F is equal to K times Q1, Q2 divided by R squared. And the unit for the charges, so the unit for the charge is a Coulomb, named after the man who came up with this law. The unit for K is a Newton meter squared per Coulomb squared, and K is equal to 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. And then R, like we've seen in other, R is in meters. Now, a Coulomb is a pretty large unit, so often we will use a millicoulomb or a microcoulomb. And I think all the problems that we work in this chapter will either be a coulomb or a millicoulomb. So if it's a so if a charge is 2.0 millicoulombs, that would be 2.0 times 10 to the 10 times 10 to the negative 3 coulombs. Okay. So let's look at a problem, and this is problem this is example 13.1 in your textbook. So what example 13.1 tells us is that you have a positive 3.0 millicoulomb charge, and you have the other particle is a negative 2.0 millicoulomb charge, and these two particles are 2.2 meters apart. Okay, so the first thing you should realize is that these two charges are going to attract each other because they're opposite. The charges are opposite, so they will attract each other. But in the equation for Coulomb's law, we do not include the charges. We just use the charges to indicate. Once we get our answer, we will use it to indicate direction. Okay, so we know what is the force between these two charges, K, Q1, Q2 divided by R squared. Okay, so K is 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. And then one of our charges is 3.0 millicoulombs. So we've got to get that into coulombs. So we would say 3.0 times 10 to the negative 3 coulombs. The other one would be 2.0 times 10 to the negative 3 coulombs. And then we will divide that by the radius, which was 2.2 meters, and we're going to square that. So 2.2 meters. Okay, so if we look at our units then, okay, the coulombs are going to cancel because you have 2 on top and you have this squared on the bottom. And these meters squared will cancel here. So we have that our force is in newtons, and that is a force unit. So the force between the electrostatic force between these particles, if you do the math, should come out to 1.1 times 10 to the 4 newtons. So what that means is that this positive charge will experience this amount of force in the direction of the negative charge because they're going to be attracted to each other. And the negative 2.1 would experience a 1.1 times 10 to the 4th Newton charge in the direction of the positive charge. So they're going to, each of the charges, they will be attracted to each other, so they will move toward each other. And so that brings up another important point, and that is when we calculate the electrostatic force between two particles, that force is true only for an instant, because as soon as these two charges are placed in the vicinity of each other, they are going to generate a force that is going to cause these charges to move. And in this case, they're going to move toward each other because the charges are opposite. And so when they move toward each other, this distance is going to decrease, right? And so that means the force will change. So the force that you calculate is really just an instantaneous force because these particles are going to move. That will change. If they move away from each other, the radius will increase. If they are attracted to each other, the radius will decrease, and that will therefore affect the electrostatic force. Okay, let's go ahead and do on your own 13.3. And the on your own 13.3, tells us that we have two charges that are 1.4 millicoulombs. And those charges are 3.1 meters apart. Okay, so electrostatic force will be equal to K, Q1, Q2 divided by R squared. K is 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. And we will multiply that times the charge of first 1.4 times 10 to the negative 3 coulombs. We need to get that into coulombs. Same with the other one, 1.4 times 10 to the negative 3 coulombs. So all we did there was divide by 1,000 to go from millicoulombs to coulombs. And then we'll divide by the radius squared. So 3.1 meters and 3.1 meters. Okay, so we'll see these meters will cancel, the coulombs will cancel, and we will be left with F. I'll go ahead and write F up here. And now, so what we get for F is 1.9 times 10 cubed newtons. And now both of these charges were positive, so they are going to repel each other. So they will move away from each other with a force of 1.9 times 10 to the 3rd newtons. And again, that force it's only going to be true for an instant, because once that force exists and once these particles move away from each other with this force, then the distance between them is going to increase, and that will change the force. Okay, so that is on your own 13.3. Now let's go ahead and do on your own 13.4. And on your own 13.4, we are told that we have two charges. We have a 3.4 millicoulomb charge and a negative 1.2, I'm sorry, these are coulombs, not millicoulombs. Okay, so this is a coulomb and a negative 1.2 coulomb charge. And now we are told that F is equal to 1.1 times 10 to the 10 newtons. And then at that instant, how far apart are the two charges? Okay, so we're basically just going to take our equation and we are going to solve for R squared. So we'll multiply both sides times R squared. So that puts the R squared over here. Divide both sides by F. So that gets rid of the F there. So then R squared is going to be equal to K times Q1, Q2 divided by F. And then R will be the square root of that. Okay, so R squared is equal to K, 9.0 times 10 to the 9th Newton meters squared per Coulomb squared times our two charges, 3.4, this is already in coulombs, so we don't need to change that, and 1.2 coulombs, and then we will divide by F, which is 1.1 times 10 to the 10 newtons. Okay, so you'll see the newtons will cancel, the coulombs will cancel, So you're left with meters squared, and when you take the square root of that, so R, to get R, we will just take the square root of this whole thing, and we will get that, and we'll be left, when you take the square root of meters squared, you're going to get meters. So if you do all that, you should get that R is equal to 1.8 meters. Okay, so both on your own, 13.3 and 13.4 are just a simple application of two charges and applying Coulomb's law to those charges and determining what force it would exist between those two charges. Okay, unfortunately, things aren't usually that simple because we don't usually just have two charges, but we usually have multiple charges, and those multiple charges create an electrostatic force. So what if we were to have a positive, let me make that a little bigger. If we were to have a positive 1 millicoulomb charge there, and we have another positive 1 millicoulomb charge here, and a negative 1 millicoulomb charge there, then what's going to happen? Well, these two, if we look at these two, they're going to be attracted to each other. So these two will be attracted to each other, and these two will repel each other. So that one would move that way, and that one would move that way. And then we could look at these two, and again, they're going to repel each other. So they would move this way and this way. So it's not quite so simple as just having two charges, but you have to figure out the relationship between what charges, what force would be generated when there are multiple charges, multiple particles that have charges. And so here also these particles are not in a straight line. So then we have to look at all the forces, and we have to figure out the vector sum of those forces. Okay, so that probably sounds a little complicated, but let's do a couple problems. We will start with example 13.2. And in example 13.2, we are given charges that are in a straight line, but there is more than one charge, or yeah, so there are more than two charges. So here is the situation that we have. We have a positive 1.2 millicoulomb, and then we have a negative 3.4 millicoulomb, and then over here we have a negative 4.1 millicoulomb charge. And the distance between these two is 1.2 meters, and the distance between these two is 2.0 meters. Okay, and we want to know what, okay, the question asks, what is the total instantaneous electrostatic force that is exerted on this charge, that particle? Okay, so we're only interested in the forces that are exerted on the negative 3.4 millicoulombs. So this problem is not so difficult because since it's in a straight line, we can just look at the relationship between the two. Okay, so first of all, these two, so we're interested in let's first look at these two. You have a positive and a negative. So because they are going to be attracted to each other, then I'll go ahead and change my color here. That means that this particle is going to move that direction because these two particles are going to be attracted to each other. And then if we look at, we're going to look at the other two as well. And because these are opposite, they are going to repel each other. So this charge will cause, this particle will cause this particle, since they will be repelled, it will also cause that particle to move in that direction. Okay, so let's deal first with the relationship between this particle and this particle. Okay, so F is equal to K Q1 Q2 divided by R squared. So that will be equal to 9.0 times 10 to the 9 Newton meters squared over Coulomb squared. And we need to change those to coulombs, so it'll be 1.2 times 10 to the negative 3 coulombs, 3.4 times 10 to the negative 3 coulombs, and then we would divide that by the distance between them squared. So 1.2 meters and 1.2 meters. Okay, so meters are going to cancel, coulombs are going to cancel, we'll be left with F. And when we do the math here, F will be equal to 2.6 times 10 to the 4th newtons. 2.6 times 10 to the 4th newtons. Okay, so that's our red. That's the force that is generated between this particle, and this particle, and it'll be in this direction. So we will write that in there as 2.6 times 10 to the 4th newtons. Okay, now we're going to do the same thing, but now we'll look at the other particle that is having an effect on the negative 3.4 millicoulomb particle. So I'll go back to black. So F will be equal to 9.0 times 10 to the 9th Newton meter squared over Coulomb squared times the two charges, 3.4 times 10 to the negative 3 coulombs, the 4.1 times 10 to the negative 3 coulombs, and then we would divide that now by the distance between those two particles. So 2.0 meters and 2.0 meters. We're squaring the R. Okay, so meters cancel, coulombs cancel, and F is equal to 3.1 times 10 to the 4 newtons. So that would be the repulse, the force that we've indicated with a blue arrow, because this charge here is going to repel this one, so it's going to move it to the left. So this would be 3.1 times 10 to the 4th newtons. Okay, so the two forces that we have are both in the same direction. So if we want to know the sum of the forces acting on this particle, since they're both in the same direction, we will add them together. So one was 3.1 times 10 to the 4th newtons, and the other was 2.6 times 10 to the 4th newtons. So if we add those together, we will get 5.7 times 10 to the 4th newtons, and we would say that's to the left, because that particle that was in the middle, the other two particles acting on it are both going to cause that particle to move to the left. And so since left is conventionally a negative sign, then we would say it's negative 5.7 times 10 to the 4th, or you could just say 5.7 times 10 to the 4th to the left. Okay, so that's how you do it when you have more than one particle acting on a particle, and you want to know the sum of the forces acting on it. Okay, now the next one is going to get a little more tricky because we're going to have our three particles, and these three particles are going to be arranged like this. So we will go here, here, and here. This is a positive 6 coulombs. This one is a negative 2. It's negative, I need a 0.0 in there, coulombs. And this one is positive 4 coulombs, 4.0 coulombs. Positive, make sure that's clear. Positive 4.0 coulombs. And then if we put distances in here, this is 0.34 meters. This is 0.48 meters. And this one is 0.34 meters. Okay, so then we need some, since these are not in line, we need some angles here. So this is a 45-degree angle. And as you can tell here, this is a right angle, so it's a 90-degree angle. Okay, and this question asks, what is the instantaneous force acting on this charge? Okay, so we're interested in this charge. What force is exerted on that charge by this one? What force is exerted on that force by that one? Okay, so first of all, these two are opposite charges. So they're the same charges, so they are going to repel each other, and so this charge it's going to push that charge that way, and these two, because they're opposite charges, they will attract, so this one would move in that direction. Okay, so that's going to be the direction of the forces. Okay, so let's look at how we would deal with this situation by Coulomb's law. Okay, so let's first look at the relationship between the four, maybe I'll draw this over here just simpler. Okay, so this one is the plus 4.0 coulombs. This is the negative 2.0 coulombs, and this is the plus 6. And this is the plus 6 is the one that we are interested in. Okay, so let's first look at the relationship between the 6 and the 4. Okay, so F will be equal to 9.0 times 10 to the 9th Newton meters squared over Coulomb squared times 4.0 coulombs and times 6.0 coulombs. And I didn't write it in here, but the distance between those, this is 0.34 meters. So we're going to square that. So F, getting rid of all the units except the Newton, F will be equal to 1.9 times 10 to the 12 newtons. Okay, and as we said, that's repulsive. So this charge will push this charge away. So we'll move in that direction with a force of 1.9 times 10 to the 12 newtons. Okay, so keep that in mind, and then let's write that one over here so that we don't lose it. F is equal to 1.9 times 10 to the 12 newtons. Okay, so that's for this particle and this particle. Okay, now let's look at what force exists between the other two particles. So now F is equal to 9.0 times 10 to the 9th Newton meters squared over Coulomb squared times 6.0 coulombs and 2.0 coulombs. And then the distance between those was 0.48 meters. So we'll square that. Okay, so again, all our units are going to cancel except for newtons, and our force then is equal to 4.7 times 10 to the 11 newtons. Okay, so we have our two forces, and since this force is going to be pushing that way, and this force because it's going to be, they're going to attract each other, so it's going to move it toward that way. So that if we look at this particle here, if we look at the particle that we had, it's going to be moved that way, and it's going to be moved that way. This would be the 1.9 times 10 to the 12 newtons, and this one would be the 4.7 times 10 to the 11 newtons. And we cannot just add them together because they do not point in the same direction. So we need to use trigonometry to be able to add the vectors together. So in order to do that, you know that you need the angles. So this angle we said was a 90-degree angle. So this one would be a 90-degree angle. And the other one, remember we always name our angles from the positive x-axis. So if this was a 45-degree angle here, then it would essentially be 360 minus 45. So this was 45 degrees right here. Okay, so if we went all the way around, it would be 360. So it's going to be 360 minus this 45, which is 315. Okay, so this would be 315 degrees. Okay, so go back into your memory now, and we will use our trigonometry that we used before when we wanted to add vectors that were not in the same dimension. Okay, so a to the x, we'll call the first one a and the second one b. A to the x is going to be that 1.9 times 10 to the 12th newtons times the cosine of 90 degrees, and a to the y write that smaller so you put it all on here. So a to the x is going to be 1.9 times 10 to the 12th newtons times the cosine of 90 degrees. A to the y will be equal 1.9 times 10 to the 9th newton times the sine of 90 degrees. And then we take our other one, b to the x. B what we calculated to be 4.7 times 10 to the 11 newtons, and we'll multiply that times the cosine of 315 degrees, and b to the y is going to be equal to 4.7 times 10 to the 11 newtons times the sine of 315 degrees. Okay, so then we will add the x components and add the y components. So c to the x is going to be equal to adding these two together. So this comes out to 0, and this comes out to 3.3 times 10 to the 11th newtons. So obviously when we add those together, we're going to get 3.3 times 10 to the 11 newtons. And then when we add the y components, this is 1.9. So this is 1. So that's going to be 1.9. And then this one will be negative 3.3. So it's going to be 1.9 times 10 to the 9th newtons, because sine of 90 is 1. So then when we add those together, c to the y will be 1.6 times 10 to the 12th newtons. Okay, so now all we have to do then is, you know from before that magnitude, all of this should sound familiar, and it's just a matter of refreshing your memory. So it's c to the x squared plus c to the y squared, and take the square root of that. So we're going to put in 3.3 times 10 to the 11th, square that, plus 1.6 times 10 to the 12th newtons, square that, and then take the square root of that, and we will get that the magnitude is equal to 1.6 times 10 to the 12 newtons. Okay, so then we have to figure out the angle. So you might remember that to get the angle, it's the inverse tangent of c to the x over c to the y. Okay, so the angle, the theta is equal to the inverse tangent of c to the y over c to the x. So it's going to be inverse tangent of 1.6 times 10 to the 12 newtons divided by 3.3 times 10 to the 11th newtons. Okay, so newtons cancel. When you take the inverse tangent of that, you will get that the angle is equal to 78 degrees. And if we look at our quadrants, okay, so the y and the x are both positive, so that puts us in quadrant 1. So we don't need to do anything with it. Our angle would simply be 78 degrees. Okay, let's go ahead and do one more example of that before we run out of time. So we're going to do on your own 13.6. And in that one, here's the drawing. So we have our charges like this. They form an equilateral triangle. So here's a charge, here's a charge. This is a positive 2.0 coulombs. This is positive 3.0 coulombs. And this is positive 3.0 coulombs. Okay, let's go ahead and erase that one and put it. Okay, so this one is positive 2.0. And in this problem, we want to know what is the charge that is acting on this one right there. So that is the one that we are interested in. Okay, so let's do the electrostatic force between, well, first of all, let's go ahead and look at the angles here. So if we draw this like this, we know that the angles in an equilateral triangle add up to so this first angle is going to be 60 degrees. So if we draw this out like that, that's going to be a 60-degree angle. And so this one also, if we draw that out, that would be a 60-degree angle here. Okay, and so those are the main angles that we need to concern ourselves with. And remember, we always measure these angles from the positive x-axis. So if this is 60, this would be 180 if it were straight out. So that would be 180 minus 60. So this would be 120 degrees angle. Okay, so let's look at the charges then. So F is going to be 9.0 times 10 to the 9th Newton meter squared over Coulomb squared. And the two charges are going to be and these two charges are the same distance apart, and they're also the same charge apart. So what were the distances again? They're 1.1 meters. Okay, so and they're also all going to be repulsive forces. So the charge between here and here, they're going to repel each other and force that particle that way. These two are going to repel each other and force the charge that way, but they're going to be equal in magnitude because they're the same size. These two particles are the same size, and they're also the same distance apart. So we really just have to figure out one of them. So we'll take the 2.0 Coulomb charge and this 3.0 Coulomb charge, and then the distance would be 1.1 meters, and we'll square that. Okay, so meters are going to cancel, coulombs will cancel, we'll be left with the force, and the force in this case is equal to 4.5 times 10 to the 10 newtons. Okay, so the attraction between this charge, or the relationship between this charge and this charge, is going to push this particle that way, and this between here and here is going to push that particle that way. So they're not in the same dimension, so then we have to use our trigonometry to figure out what the resultant vector will be. So we will start with A. So A to the X and A to the Y, B to the X and B to the Y. And then we'll sum those to get the C to the X and the C to the Y. So A to the X would be the vector that we calculated, 4.5 times 10 to the 10th newtons, times the cosine of 60 degrees. And over here would be the same thing, 4.5 times 10 to the 10th times the sine of 60 degrees. And then down here it's going to be exactly the same, 4.5 times 10 to the 10th, but now it's going to be the cosine of 120 degrees. And this will be 4.5 times 10 to the 10th times the sine of 120 degrees. So this is equal to 2.3 times 10 to the 10th newtons, and A to the Y is 3.9 times 10 to the 10th newtons. And then B to the X is negative 2.3 times 10 to the 10th newtons. And this one is 3.9 times 10 to the 10th newtons. So when we add the X dimensions together, here we have a positive 2.3 and a negative 2.3. So C to the X is going to be equal to 0. And so that means that the vector will not have an X component. So the y components are going to point in the same direction, so we're going to add those together. So 3.9 and 3.9 will give us 7.8 times 10 to the 10 newtons. Okay, so in the end, this really is just a one-dimensional vector then, because there is the x component, there's no x component, and there's only a y component. So for this particular problem, the vector will point straight up, and it will point straight up at 7.8 times 10 to the 10 newtons. Okay, so there is no x component for that. Okay, so that is all we have time for in module 13. There's more information, but it's not that, I think we got through the most important things. So the practice problems that you should be able to do. So don't worry about others except for these. You need to do number 1, number 2, number 3, number 4, number 5, and number 6. I believe that might be it. Yes. Okay, so 1 through 6 are the practice problems that you should be able to do, and I will record those solutions on a separate video so that you can see how those problems work.